I'd like to thank you all for coming to the MIT Global Boston's Boston Seminar Series. And my name is Linda Genovicius Morales, and I'm the current chair of the Boston Seminar Series Committee and a past president of the MIT Global Boston. The MIT Global Boston is an independent, nonprofit, member-supported, volunteer-run organization for MIT alumni, students, affiliates, and their families living in the Boston area. And we support social networking, educational, and service opportunities in the Boston area for the MIT community. And I want to thank all the members who have come here today, and thank you all non-members for coming to see this. And almost all of our events are open to the general public. So please check the website at boston.alumclub.mit.edu for updates. And we're always looking for volunteers and ideas. So please contact me or anyone else in the club for more information. Really quickly, our next event for the club is going to be next week on Wednesday. It's a book discussion group with Matthew Pearl, who wrote The Technologists. And it should be an interesting event. So if you can make it, please check the website and you can sign up there. In February or March, I'd like to try and do a dinner format of the Boston Seminar Series, which is similar to what we used to do a couple of years ago. And it's going to be more expensive because, believe me, you can't get any dinner for catered for less than like $60 to $70. So it's going to be that price range, but it should be good. I'm hoping to get a good speaker, possibly Don Sadoway, and we'll see. So please keep checking, and I'll be sending emails for sure. And then on May 6th is going to be the final VSS of this school year, and that's going to be downtown, and the speaker will be to be determined. We're not sure yet. All right. I'd like to thank Wilmer Hale for their support of this PSS lecture, and Wilmer Hale provides a broad range of legal representation to its clients, and the firm is a leader in pro bono representation with over 1,000 lawyers among 14 offices in the US, Europe, and Asia. I'd also like to give special thanks to Microsoft New England for hosting this event, and we really appreciate both of their support. And also, you may have noticed that we're videotaping this lecture, so I think generally we're not going to get anyone in, but if you do ask questions, you probably will be recorded. So if you don't want to be recorded, you could just say so at the beginning, and I can cut you out when I edit the videotape. Right. And I'm also pleased to say that our website has been inaccurate. Professor Vladimir Bulovic is now the Associate Dean for Innovation in the MIT School of Engineering. So this is a new promotion. So please congratulate him. And he will be supporting innovation and entrepreneurship. It's a new program at MIT. And he will co-direct the MIT Innovation Initiative and is the faculty leading the design and construction of MIT's new nanofabrication, nanocharacterization, and prototyping facility. Vladimir directs the Organic and Nanostructured Electronics Laboratory, which he developed as a unique open nanotechnology facility. He's also co-directing the MIT Solar Frontiers Center, among MIT's largest sponsored programs. Prior to joining the School of Engineering Leadership, Vladimir directed the MIT Microsystems Technology Laboratories. And I could go on, and I deleted about a page of other accolades. But I won't tell you any more of his accomplishments, since I'm sure that you prefer to hear him speak. So on that note, please welcome Associate Dean Vladimir Bulovic.
Thank you. Thank you. Well, thank you very much. It's a pleasure to be here. Does this work? No. No? Who knows? I have a whole bunch of these things. So try this one. That says mic. That works.
Okay,
that's on.
We have another one.
I can also just speak loud. Is that right? I'll do my best. It's only an hour. And indeed, if you can't hear me, please raise your hand, and we'll try to figure out the parts here. So it's a pleasure to be here. Thank you very much for having me. My job, I think, for this afternoon, evening, is to provide you a light pre-snack or pre-dessert experience. I'll do my best by telling you a few things about nanotechnology because it's small and that shouldn't take very long. But I do think that there is a tremendous amount of things to be done. And indeed, I guess the way I would start is maybe simply to emphasize that we have spent as scientists and technologists about 2 decades trying to see the nanoscale, trying to understand what's down there on the bottom, and we've developed a whole slew of tools to poke molecules around and untwist the nanotubes and see the graphene sheets. And, you know, we love every single element that we have discovered. And yet there are seldom few examples of taking the nanotechnology and actually making it into a practical technology. So I guess I would say, just like science led eventually to engineering, we are poised to take the present understanding of the nanotechnology and take it one step beyond and actually go ahead and enable the 21st century through coming up with a variety of new ways of nanomanufacturing that go ahead and exploit, call it these fundamental findings on the nanoscale. It takes a step beyond of what we think might be possible, right? So my building blocks as I chat with you today will be to use molecules or quantum dots. I am an electrical engineer, just so you know. That's perfect. All right. I won't yell anymore. There we go. All right. So the goal is to go ahead and take these building blocks of nanotechnology we developed over the past 20 years and do something with them, like this. So here is an example of your solar cell that you'll have available in your store near you in a couple of years. Well, no, it's probably going to take more like 5. But you'll have the ability to start thinking about entirely different ways of thinking what solar cell can do for you. Now, what this is an actual sheet of paper that's been painted with 1 conducting thin films through a process of chemical vapor deposition that Professor Karen Gleason at Chemical Engineering develops. And then electrical engineers like myself can take the credit of this fantastic chemical work by adding to it a few extra layers. And the stuff that we do is we go ahead and we take molecules, dyes that actually are used to paint Ferrari red, and then add to it a little bit of the blue paint that paints Smurfs, like that. It is actually, it's the same paint you would use, telecyanines, that you would use copper telecyanine to go ahead and get yourself a nice blue color. And between these two semiconductors, and I use the fancy word, molecules are semiconductors just like silicon is. We don't usually think of them, but you know, the age of 1960s, before we established silicon as being the king, organic semiconductors were just as valid of an option. We forgot them and left them aside, only to rediscover them in the 1980s when we made the first organic LEDs. Now, these days, those of you who have Galaxy phones, Samsung Galaxy phones, enjoy the benefit of organic LED displays, where I'm going to talk a lot more about those because I have a passion for them in my own way. But you can take that very same idea of organic LEDs and run it backwards. Rather than apply electricity and get light, you can shine light and get electricity out of it. That's known as a solar cell. All you need is what is known as a heterojunction, which simply means put together 2 materials of different types. Make sure the energy align just right so that when you excite one of them, you can give the electron to the one leaving the whole positive charge on the other. Separation of charges generates electric field, integrated, and you're going to get voltage. That's the open circuit voltage of your solar cell. All you need to do is separate charges. And the easy way to do it is make molecule type 1, molecule type 2, evaporate them on top of a piece of paper, slap on an electrode. You don't really slap it on. You evaporate another layer of metal on the top and measure voltage between the top and the bottom. And you're going to get yourself what I think is a universal PV, one that is lightweight, modular, and can be integrated. Now, exactly how you do this, here is the chemical vapor deposition process of Karen Gleason's, and she can go ahead and evaporate these electrodes that start the whole process on magazine print, on post-it paper, tissue paper, wax paper, t-shirt fabric. You choose it, she can do it. And then we evaporate some of those organic films, car paints, followed by a cathode up on the top. and you have yourself a device. This is about 0.3 microns in thickness. To get you a scale of things, your hair is about 50 microns in thickness. So 0.3, that's about 150 times thinner than your hair. And then go ahead and deposit this over as large of an area as you want, akin to the way that you would use the same techniques for coating, let's say, my pants, so that you make them a nano pants, right? The nano pants are really pants that don't stain, that have thin films, essentially of Teflon, also developed by people like here in Gleason, that can conformally coat surfaces, also utilizing semiconductor technology tools, but now deploying them over larger areas of surfaces that we might want to use in the form of fabrics. This, I'm just suggesting, might be one step beyond the conventional fabric or conventional surface. That is to say, it might not just be pretty and stay unstained, it also might be able to generate electricity. Why do you want to do that? Well, any surface would benefit from a little bit of electricity. Is it to actually make it active as an electronically active element that thinks? Or is it to sense you're touching it? Or is it to speak back to you? Is it the variety of options? And we can mention a few as we speak. Now, what I'm showing you here, I'm an electrical engineer. I really do applied physics as I think about the world. I talk to chemists and material scientists, and I'm willing to be the ambassador between these fields, as I think the clues to what's happening next really lie at the cusp of the fields and at the ability to converse between them. Often, we just actually don't recognize us chemists, well, us electrical engineers and them chemists, we don't recognize we're talking about the same thing often. So to us, dipole-dipole interaction, to them it's a forced or resonant energy transfer, whatever that means when they say whatever that means when we say it, when in fact we're talking about exactly the same phenomenon. Go figure. Now, that being said, you can go ahead and take these molecules and put them on a piece of plastic, apply some light, and you're going to get this diode-like behavior. This is a solar cell, this solar cell in plastic in dark, and this other one is the same solar cell but now illuminated. The only thing you need to know is that the two curves look different, and that's good. The other thing you need to know is that you want to have a lot of displacement from the first curve to the next. And the third thing you need to know is that if this is really truly a flexible, conformable, durable device, if I flex it once, it should still perform the same way it did before I flexed it. If I flexed it twice, it should still perform the same way. As a matter of fact, you can hire a graduate student, and you can ask them to flex it 100 times, and they do. And you can compare the 100th flex, which looks exactly the same as the very first time you measure the device. This is a very durable device. You cannot do this with conventional other transparent conductors, such as metal oxides, because they would crack. These don't, because they are covalently bonded to the underlying substrate. The one thing I'm not showing, because it would be embarrassing to point out, but we did ask the student to flex this 1,000 times, and they did. And it still works, just the same as well as 100 times, but we don't put a data point on there. It might be misinterpreted. The other thing then to do is actually to demonstrate to you that this piece of paper actually can power something. So here is that same piece of paper connected with a couple of electrodes, and I'm powering that little electronic clock in the back as I shine light on it. Now, this is a very different kind of solar cell. As a matter of fact, let me see if it acts like a real piece of paper. One way to test that is insert it in a laser printer. A laser printer is a really good stress test. It reaches up to 250 Celsius. And I'm going to choose to fuse the toner right on top of the cell. Now, this thing really shouldn't work anymore because that's a fairly high bit of abuse. But shine light and it still works. So your conventional idea of what a solar cell is has nothing to do with this device. As a matter of fact, if you try to raise money today and ask a VC to fund the solar technology, they'll say there's no way. Because why would I ever invest in a field that is so heavily invested by China and overproduced? Well, this is not a solar cell. This is a replacement for a battery. This is a power source ubiquitously deployed on any surface. It has nothing to do with your common notion of what a solar cell really is. Because now I can imagine that same solar cell being on a dollar bill. Why? For security reasons. Maybe I want to have a fancier advertisement. Maybe I want to have a power code here to be able to inform the wirelessly the scanner, so you don't actually have to scan it, but it speaks back to you. Or maybe this unit right here is actually what excites me probably the most. And that is to say, the important metric here is this is an extremely lightweight solar cell. Is it particularly efficient? No. I mean, it's efficient. The best ones we made today are maybe 3% efficient. We can see going all the way up to 17% one day. But that's not what excites me about it. The metric that I care about is not efficiency. But what I care about is this watts per kilogram. This number of watts per kilogram excites me because I think this is the defining metric for the deployability of a solar cell. If I ask you what matters for a solar cell in the deployment, you say, well, I just want to make sure I can install it as a large field outside my town, and that will be my solar field so I can go ahead and run it. Well, that's not why you would make solar cells today. Indeed, this will not compete with today's solar fields. But if I go ahead and ask you, well, where are solar cells needed? To us? Well, yes, we are trying to avoid CO2 emissions because we burn too much coal and natural gas. That's absolutely true. Are we going to install a solar cell? Well, no, until it gets really commercially competitive. Why would I do it? And indeed, there is at least 10% of US electricity market today that without any subsidies, silicon solar cells can be competitive. So yes, maybe you'll install them there, but not these. Where solar cells really matter are places that have no electricity, places outside of the United States, places likely that don't have grid, and hence have no access to power. So an example would be Africa, where there are 50 million new cell phone users every year that have absolutely no access to grid electricity. 50 million. So why do they buy the phone, right? Well, they buy the phone because it turns out that if they walk 2 hours to a neighboring village, wait for 2 hours to have the phone charged, and walk back to their own village, in 6 hours they can charge their phone. For that privilege, they'll pay 25 cents, which translates to $250 a kilowatt hour, given the amount of energy you actually happen to put inside the phone. About 1,000 times more expensive electricity than we pay. And they need it because when they fish down that river, if they choose the wrong village to sail to, the fish might spoil before they realize that. So they want to know, they want to call ahead of time and say, do you need fish upstream or downstream? And I'll go and sail the right direction. So to them, the livelihood very much depends on the cell phone technology. But since they have no way to charge it, well, maybe one way to do it is the cardboard box in which the phone arrives could actually be the charger if the surface paint happens to be solar active. And from that perspective, if I ask you, well, is this really a viable technology? Well, this thing is viable because it's going to give you power for the next 2 to 3 years before it decays or you rip it. Well, is that better than silicon? It turns out it is. Anecdotally, silicon solar cells in the field last only about 6 months. Why? Because they're the most expensive thing in the village. So why? Because they get cracked in the process of delivery. There are no roads to actually reach these villages. And so from a perspective of a donkey carrying a solar cell to the village, that donkey doesn't care about the efficiency of your solar cell. That donkey only cares about the number of trips it needs to make back and forth. So give me most watts per kilogram, and I'll make the largest impact, both in shipping costs and in the delivery costs. The making of the module doesn't cost us very much. Today, even in the developed world, nearly 2/3 of the expense of solar cells is in the deployment of the solar cell. And a lot of it actually is in the regulation, in the fact that the government needs to approve a certain piece of paper before you can install your solar cell in your field or on top of your roof. In Germany, that's not the case. They have one piece of paper, and it's about 1 page, and the whole country has it. So in a matter of a week, you can get an approval. In the United States, we have 10,000 different regulations. Every municipality has a different if you live in Belmont, you can't put solar cells on a side of the roof facing the street because apparently they don't look very good. But if you had these, no one would know, right? These you can go ahead and stretch and staple to your roof. No one would know, right? The other thing to ask is how lightweight are these? Because, from all me telling you these are lightweight, is there a metric I can give you? Indeed, our job is to be the honest broker in the process. So here it is. This is a technology that was last year developed following our work in University of Vienna. They looked at 1.4 micron thick plastics and then coated them with organic dyes. Here it is that solar cell wrapped around a strand of hair. And here is the watts per gram that you can generate of that solar cell compared to all the other technologies. These are cells. That's not fair because cell needs to be packaged and then actually deployed in some way. So compared to a module, here's a module. Ooh, module is a lot less, but this is a 1.5 micron thick cell. It's going to rip. So how do I fix that? Well, take 2 pieces of plastic, 100 microns each, 4 mils, laminate on both sides of this 1.5 micron cell. Oh, I just increased the weight about 200 times. What does that do to my performance? Well, it brings me down here. Oh, look at that. That module, organic flexible module, happens to be still a factor of 5 more watts per gram than any other technology ever developed, even in this very, very early days of making, relatively speaking, inefficient technologies. So it seems to me there is an opportunity to think about an entirely new format of what solar really means. How about the next one? Here's another one. This is a solar cell it looks like absolutely nothing. And as a matter of fact, we made this back in 2011. I had an ABC News science reporter, weatherman, come by to interview us about this technology. I said, film it. I said, well, there's nothing to see, man. It looks just like a piece of glass. And it does, because it turns out it doesn't absorb any light in the visible part of the spectrum. But it does absorb light in other parts of the spectrum. So it turns out, as such, this is an invisible coating that converts light to electricity. It looks pretty cool. It's aesthetic. It has the performance. The official name is Clearview Power. A little company called Ubiquitous Energy is looking into commercializing this and thinking about how do you actually extend what we conceive of solar cells to be. So one way to ask, well, how do I make this thing? Because it looks so cool, right? Is to go ahead and say, well, today's windows, these windows, are not 100% transmissive. That's on purpose. We put coatings on them to prevent infrared light, but also to dim a little bit of the image inside compared to viewed from the outside. Typically, a typical office window is 55 to 80% transparent to visible radiation, to any radiation coming in. Well, visible radiation is what we see. Infrared gets cut off even more. How do you do that? Well, you can do it with silicon, make a solar cell that might do this, but the thing with silicon is that this is a wavelength as a function of intensity of absorption. So silicon starts absorbing in infrared, and then all these are colors in the visible. You absorb more and more and more. So the only way you're going to be able to do this with silicon is to make it extremely thin and make it not absorb any light anywhere. Now, that's not good. Another option is to go ahead and utilize molecular dyes. Molecules, I mentioned blue telecyanines. Copper telecyanines happen to be blue. But if I give you chloroaluminotellocyanin, chlorine aluminum attached, the same kind of bit in the middle, you can actually make solar cells that absorb only in the infrared part of the spectrum. This is the infrared. You mesh it with buckyballs or derivatives of buckyballs, and you can have a structure. It looks kind of like this. These are the layers. You start with a piece of glass. You put some indium tin oxide, evaporate a couple of more films. The whole structure here is half a micron thick, and you finish it off with a transparent electrode. This is how it looks when you finish it. And then you go ahead and look at the absorption spectrum, and that's the black line. That's the light that I absorb, infrared, and some of the UV. I happen to exactly miss the visible part of the spectrum. Why? Because I have really good chemistry friends, and they know how to engineer the molecules. Molecules can be precisely tailored to give you any absorption spectrum you choose. And then, as an electrical engineer, you can recognize you can actually use this as a semiconductor and utilize it for what? Well, here are examples. I can go ahead and take that very same solar cell. Here it is. Oh, here it is. It's powering this little electronic appliance, just like the other one you saw before. I can take that very same film and coat it on top of a Kindle. Why? Because I'll never have to recharge my Kindle again, ever. Because the trickle charging, even from the room light like this, it would be sufficient in the course of a week to recharge your Kindle. It has a battery that lasts 2 to 3 weeks. Outside, it's half an hour of standing in the sunlight to charge it all the way up to the full. That's plenty. There's plenty of infrared radiation. What's your relationship to your Kindle at that point? Do you hate it because it's discharged? Well, never again, right? You'll always now relate to your appliances in a very different fashion. Every surface you touch now can be active. How about my phone, iPhone? Well, iPhone uses too much power. So does Google Android, by the way. But the point is, nevertheless, if my battery ever runs out, I leave it in the sun for half an hour, and I will actually get an ability back to turn it on and use it, because I'll be able to trickle charge, extend its lifetime from 2 to 3 days, maybe to 3 to 4 days, because I happen to choose to use it. I keep my phone in my pocket. That's not the best use of it for charging, but if I need it, I would have that option. And would you know that the technology is there? No. I just added a micron-thick film together with the electrodes, a micron, half organics and half the electrodes, on top of your Kindle. Would you know it? No, you wouldn't. Would it weigh much? No, it's micrograms of power. So indeed, there is multitudes of options. How efficient can you make a technology like that? Actually quite efficient. You say, well, it's not absorbing very much visible light. Well, those of you who are technologists, I can convince you by asking some rational arguments of what is practically achievable. You know, there's a Shockley quasar limit. You might have heard if you're a solar enthusiast. This is the absolute maximum one can expect out of performance of a solar cell. And for silicon, that should be 29%. Silicon, after 4 decades, has not reached 29%. It reached 27.5, right? I cannot expect that my technology, barely a couple of years old, will reach the Shockley quasar limit, but I can expect to discount it in a number of rational ways. And rather than reach the high number, I can expect much lower performance. But you know what? Single junction cell like this should be able to reach 12%. 2 junctions, meaning two different infrared band gaps, I should be able to reach 17%. Again, those of you who are solar enthusiasts would recognize these are actually competitive numbers with any silicon or CAD telluride technology deployed today. And yet I offer it in a very different format, one that you cannot see and cannot perceive. Now, to me, Kindle is a first stepping stone, because I'm not going to save the world with Kindle. I'll change your relationship with your electronic appliances. But my hidden goal really is to help the world. And the way I'm going to do that is to say, well, Kindle, how long does it last before your kid might break it? 3 years before accidentally someone sits on it? So that's the lifetime of my solar cell. Typical electronic appliance in your home has a lifespan of about 3 years. That's the expect. If you stop working very well after that, that's okay. No one expects your phone to last more than 3 years. That's fine, because my technology is brand new. It does last today 3 years. I need to learn how to make it last 20 years. And I know I can do that because, again, I mentioned I have this passion for organic LEDs. The first time I was making them, back in '94, they lasted 1 hour. 3 months later, we realized we can take a nitrogen package, which is simply a glass lid with a 5-minute epoxy, and we extended the lifetime all the way up to 1 month of operation. And then we kept on working. By the time I was done with my graduate work, we had it at 100 years operating lifetime. Because we've realized what makes these things tick and how to increase the operating performance. All those lessons, plus more, that we now understand on solar cells, we can apply, and one day hopefully make cells that last 20 years at least. And hence, I should be able to use them as coatings on windows. Why? Because if I can give you a building that actually has the side of the building coated with solar cells, in the morning and in the evening, you can capture a tremendous amount of electricity. And the tremendous amount of electricity translates with a 5% efficient cell to 25% of electricity of a typical office building. That's a significant energy impact if I can provide it as a norm. And indeed, there's a significant market you can develop from that, if that's what you want to do with it. The other thing to point is that if you look at the actual progress of the solar technology increase, organic PVs from 2000 on have done a dramatic change. We were down here at about 3% when we started a decade ago in the field as a whole. And today there are numbers like 11% shown for organic PVs. These are not transparent ones. These are the conventional organic PVs that absorb across the entire visible spectrum. In tandem, over the past 5 years, we developed a series of quantum dot PVs. I'll just alert you to this data point right here and the name next to it. Accidentally does happen to relate to our lab. We have just made the world record last Thursday. The world record quantum dot PVs. Again, through understanding the basic physics of why technology works, by asking very simple things of what are the band lineups, what are the energy levels, how do we increase the operating performance by charge pileup, and essentially linking the chemistry with the good old electrical engineering and good old quantum mechanics that goes in it. You can go ahead and come up with a variety of advancements that advance practicality of technologies like this one. These technologies, you should be able to, when you absorb across the entire visible spectrum, rationally reach 17% for single junction and 24% for the tandem. There are a variety of other considerations you should have. I'm not going to belabor them besides one fact, which is, if I look at all my organic structures, they're typically made of carbon. Or if I use quantum dots, I might use lead and sulfur, lead sulfide or lead selenide. Those are both abundant material sets, largely deployable, easily deployable over large areas. And concerns of poisonous of lead can be managed if you go ahead and have a surface you can package. Organics, though, are primarily carbon-based. So I can ask a very simple question. Do we have enough carbon to make significant impact on the world electricity market? And I can say, let me say, I can generate 10% efficient cells one day, and I'm going to go and reach 10 terawatt electricity production. Now, 10 terawatts is more than we need, but for the entire world, but plenty. So 10 terawatts is where I'm going to go for. How much coal would I need? About 10 to the 7 kilograms of coal. How much coal do we mine in the United States every year? About 10 to the 12 kilograms of coal. All I'm really saying is that if you want to make a lot more money on coal, it's much better to convert those carbon atoms into solar cells than to sell them as coal. Now, that's not quite true. You make it up in volume, right, when you go ahead and sell coal. But the one much better way of using those atoms, indeed, if I burn a chunk of coal, every carbon atom will give me about 2 to 4 electron volts of energy. Every time a photon shines on my solar cell, I get about 1/2 to 1 electron volt of energy. A solar cell, well, it can take photon about 1,000,000 times per atom. Burning, once. So you can get, for every atom, several million electron volts of energy in a solar cell, and about 2 to 4 electron volts of energy if you burn it. Your choice. Oil is even a better choice to look at, simply because oil is really a really good starting material for it. Petrochemical industry really enables our organic electronics as we know it. Now, I'm not supposed to show you this image. This is iPhone 7. But it is enabled by, it's not iPhone 7. I just took it off the web. But it does actually show what we should be able to do through the use of the nanomaterials. And indeed, that brings me to my other passion in display technologies, looking at ways of making organic displays work for you. I started as a graduate student making the very first ones. This little company called Universal Display Corporation got started from the patents generated in my advisors group, Steve Forrest over at Princeton, and now he's at the University of Michigan. Myself, my colleagues like Professor Mark Baldock, who's here at MIT, and others around the world, generated a huge number of technologies related to organic LEDs that spun out a company called UDC, now publicly traded, and indeed the key to the phosphor reds and greens inside the Samsung Galaxy phones. You look at those, that's UDC, that's United States technology. Now, you look at that particular technology and you say, well, this looks fantastic, but how come Samsung is not making bigger phones? I mean, they're making Samsung Galaxy and the Note, but they don't go this big, or they don't go 55-inch. They could, except they would charge you about $25,000 for a 55-inch screen, and they would still lose money. And the reason for it is really you. The problem is that you are so finicky when you look at the display. You want every single pixel to work. I mean, how unreasonable, you know? As a matter of fact, and I tell you, you know, you're not very forgiving in the display industry, because you are very forgiving in everything else we do. Like, you know, the guys who made the Pentium chips inside this processor, you know, the Pentium, Intel Pentium, 5 to 10% of transistors inside that processor do not work. But you don't care. You don't care. You know why? Because Microsoft and others who program this thing come up with clever ways to have redundant operations, to double check and actually circumvent the non-operating pieces. If I gave you a solar cell, do you know that fraction of those panels do not work? You wouldn't know. They look just the same. But you stare at the display, and every one of those 4 million subpixels better work for you. If there's one bad one, I can sell it. You know, there are a few people who won't notice it, so we sneak those in. But if you have 2 bad pixels, forget it. You're entitled to a new display. As a result, if I ask you what is the yield that I need to generate, and mind you, I'm making organic LEDs. The structure of organic LEDs, this is 100 molecular layers of material, 100 molecular layers. And you know what? The middle 10 molecular layers are the ones that are glowing to give you that image. That's the thing that's being excited by the 5 volts you apply on the outside. And you want me to put these 100 molecular layers over an area that's the size of this table, or that way bigger than the size of that window? And the answer is yes, you do. You want me to do that, because you would like a display that big, and you want every one of those pixels to work. Well, that's hard. So we started back in the 2000s with a variety of ways of manufacturing these. And indeed, Samsung has invested several $1 billion trying to come up with a technology that surpasses the simple one. And the simple one that they still use today is a shadow mask. A little piece of metal with holes in it, and they move it to the left and evaporate the green material, and move it to the right, evaporate the blue material, move it more to the right, evaporate the red material. Move it, shake it from all the dust, try again. Yield of that process is 90% or thereabout. So if I want to sell you a display this big, double the size of display, the yield is 90% squared, comes out to 81%. Double that, 64%. Double that, 36%, and so on and so forth. By the time you reach a 55-inch screen, you're at 5%, 10%. So if you're willing to buy 20 screens knowing one will work, fine. You know, we have a business. And hence why I need to sell it to you for $25,000, because I need to throw away 9 of the 10 screens. So coming up with a better manufacturing technology, indeed, is a dramatically important thing to do. And OLEDs, though, are a fantastic platform. If we can fix OLEDs, we can fix anything in the nano world. And organic LEDs exemplify that first attempts in nanomanufacturing, large area nanomanufacturing, that we're going to start seeing much, much more broadly deployed as time goes on, because the accuracy, again, needs to be at the accuracy of a fraction of the 10 molecular layers, which is roughly 2 molecular layers. I need to give you 2 nanometer smoothness over an area that's 2 meters squared. That's 1 to a billion ratio of the width to the thickness. And we can do it once in a while. We are, another technology we launched from MIT, this is back in 2008, a student of mine said, you know, things are going well and I want to have a job, so let's collect the patents. Actually, this technology of printing that we developed emerged from a partnership with a company. You might have heard of it, HP. So HP funded MIT in a partnership with Microsystem Technology Labs as investing about $1 million a year for a variety of things that would support their desire to do printed electronics. Indeed, we developed a set of printing tools that they started adapting only to have a change in their CEO who said, forget printed electronics, we're going back to basics of printing and software. And as a result, the patents just stood there. We approached Sam Angeles from HP Corvallis, who runs the division of the hardware printing, and said, you know, Sam, do you guys need these patents? And he said, no, we're not going to use them. You take them. My student raised about $10 million. We started a company in Palo Alto, California. They have about 50 people now. And they've been, at this point, raised maybe $60 million developing tools that are as big as, well, there's a human here on the side. This is a human that is developing printers that can print, in this rendition, 1 meter by 1 meter piece of glass. But what is about to be rolled off, and I don't have an image of it because it's still proprietary, but here's a rough speaking sketch. Here's a human. This is the machine that they're developing. It's the size of this room, and it's able to manipulate a 2.5 by 2.5 meter piece of glass. Why? Because you want to make a single deposition and then slice this into 8 55-inch displays, for example, or 6, depending on how big you want to make your display to be. What costs you money in display making is how much time it takes you to make a display. So make a bigger chamber and manipulate bigger pieces of glass, and you'll be able to reduce the costs. That was the drive that people have seen. So this is OLEDs, and you know, indeed, this kind of tool might be the solution that will enable OLEDs to be delivered in a format of very large display surfaces, because we have this ubiquitous desire for observing images. 99% or 90% of everything we perceive in daily existence is through our eyes. So our desire for displays is insatiable, especially ones that look really good, ones that give you very deep blacks and very bright and saturated colors. Because that contrast between a dark and light is what gives the depth of the picture. If it acts fast, if this image is able to shift very fast, then I can maybe interpolate several images, one after the other. As a matter of fact, one of the demos on the latest Consumer Electronics Show was, I think, from Samsung or LG. You can buy a pair of glasses that look at your organic LED display, and you and your spouse can watch different TV channels at the same time on the same TV, because she or he would see interleaved images in between your programs. So every other screen is different, and the flashing of the shutters in your eyes will project, or you can actually do it up to 10 channels. And so you can have a family viewing experience. But it comes from the fact that the OLEDs can respond about 1,000 times faster than liquid crystal displays. And the energy efficiency also can be dramatically better. And that's indeed the graph I showed a moment ago when I showed the consumption of energy in a typical liquid crystal display compared to an OLED. That's why OLEDs one day will indeed, once they can be manufactured, will indeed take over from the LCD industry. Today, though, the LCDs are the king. And indeed, 90% of the displays are liquid crystal displays. Mine, indeed, over here is one of them. And nanomaterials still play a significant role. And actually, you probably are aware, liquid crystals, those are organic molecules. They're about yay long. You know, that's 3 nanometers, maybe 5, and then a nanometer wide. And they twist around. They generate they modify circularly polarized light in conjunction with polarizers. And from that way, you can have light passing through, then twist and meet the opposite polarizer, or not twist and pass through. So those are the options. So a typical display allows you to, liquid crystal display uses nanomaterials already to actually give you what you observe. But there's one other thing that would really be good to be enhanced with nanomaterials, and that is a color of light bulbs that happen to sit behind the display. So allow me to show you that. Oops. I'll tell you how we do it at MIT. How do we change the color? Professor Munji Bawendi is the wizard behind the ability for us to change the color. Again, notice pairing up of an electrical engineering professor and a chemistry professor, because it turns out that, again, my job is to benefit from the wisdom of my colleagues as I do the last step. They like to do all the hard work. They like to do all the nanomaterials. We do the last step of taking those nanomaterials, engineering the device, and actually putting the nanomaterials in an active way that enables these materials to shine beyond what they were just in a beaker when they were made. So what these are so colloidal quantum dots, are little chunks of stone, crystals, that are three-dimensionally bonded. So you can think of them as molecules, but every molecule I've ever worked with, you can draw on a piece of paper. So that means they are two-dimensional objects, because I can make a piece of paper and rip it, right? I just split the molecule in two. If I give you a quantum dot, it's a three-dimensionally bonded. In every direction, there's a bond. So this structure is much more robust. You can't easily split it. You can't easily rip a bond and rip out an atom. Much more stable as a device. And one other remarkable thing about it is that, and I'll tell you a little secret that we don't teach anyone except when you get to like junior, senior year, but really we should tell our high school students, even middle schoolers. It turns out, you guys have heard that photons are waves, and photons are also particles, right? We are comfortable with that. We call light is made either of the waviness of electromagnetic waves or these chunks of energy known as photons, right? If I tell you that electrons are particles, you're okay with that, because you have always been told they kind of fly around like balls around the nucleus, which is entirely inaccurate, but there it is. The other thing that I should tell you, and I should have told you all along, is that just like photons are waves and particles, electrons are also waves and particles. Electrons have a wavelength, just like photons have a wavelength. Their wavelengths are very, very small, only a few angstroms in dimension. But because of it, if I give you a box that can contain that wavelength, I can affect the energies of those electrons sitting inside that box. As a matter of fact, a resonator, optical resonators, is two mirrors that happen to be a part that corresponds to the distance, to the wavelength of light, typically half a micron, right? If I give you a box that's a resonator for an electron, it better be of the size of a few nanometers, because that is the wavelength of the electron. So I'll give you a small box, and the box I'm going to call the quantum dot. Why? Because it sounds cool. You can also call it nanocrystal. The little quantum dots, little chunks of stone, give me a small dot, and the wavelength will be very short. And short wavelengths, just like when I play a violin and I press the string, the wavelength is short, sounds like a high pitch. If I give you a long string, it's low pitch, right? So choose the size of the box and you choose the pitch, the energy of the electron. As a matter of fact, you choose the spacing between the energies of the electron. So by choosing the size of the box, I can choose small box, big spacing. Open up the box, the wavelength increases and the spacing between the filled energy level and the empty energy level decreases. This is known as the band gap. And when I excite the electron up here, and when it relaxes back down, that relaxation gives off light. So the size of the box can tell me the color of light I'm going to get out of my quantum dot. Brilliant, because it's physics, it's not chemistry. So from perspective of electrical engineers, I can understand this. All I need to do is take one of these quantum dots, one of them, any one of them, as long as that you can give me other ones in the same family. And if I can chemically optimize my devices for one of these dots, then any other dots in the same chemical family, meaning just different size, but same chemical ending on the outside, should work inside my device. So quantum dots are these little chunks of stone. They have fantastic opportunities. One of them is that if you happen to make them just right, and the just right came in the early 90s. Professor Munji Bawendi worked in the late 80s, early 90s with Louis Bruce at Columbia, and he made first quantum dots with him. Him and Paul Alvasados, who's now a well-known professor over at Berkeley. So Munji and Paul were making some of these nanocrystals. Munji came to MIT and realized that he can make them really, really bright by taking a quantum dot and putting a shell, a single atom thick shell, around the core. And that's what this picture up on the top indicates. There's the core, a little chunk of stone, and then a shell of single atomic layer thick, again, inorganic material that passivates the dangling bonds of the core. Dangling bonds generate what are known as the mid-gap states. Mid-gap states quench your excitons. Excitons are what you need to get the light. So get rid of these dangling bonds, you'll do really well. Once you have the shell, you still have dangling bonds on the shell. That's okay. What we'll do is attach some organic moieties on the outside. So this kind of looks now like a tennis ball, kind of fuzzy on the outside, gooey, greasy, organic looking, and hard on the inside. And that's what a quantum dot is. From the outside, it appears like an organic molecule, but really has a heart of stone. And this heart of stone is what gives it the luminescence and the stability that you can observe. Choose the size of your quantum dot, and you can change the color from blue to red. This is for cadmium selenide. You can use it a variety of other material sets to generate any color all the way across visible and into the infrared. You take a quantum dots, and they come as this liquid. Now, these are little chunks of stone that are floating inside a solvent like hexane. And go ahead and spread this liquid across a piece of glass. Why? Because I want to fix light bulbs. So here is that piece of glass, hexagonal shape, because we like hexagons. And we coated them with quantum dots and then put another piece of glass on top. You can shine UV light in this piece of glass, or blue light, and this glass will glow whatever native color of the quantum dot is. Why do I want this? Well, because I'm not satisfied with my light bulbs today. And the reason why I'm not satisfied with my light bulbs today is because I really don't like the color that they give. Today's LED lights are very efficient, much more efficient than incandescence by about a factor of 7. A little bit better, about almost factor of 2 better than fluorescent light bulbs are. But color still really bothers me. And the reason why is very simple, and that is that today's LED lights are the blue LED, that's this blue peak, and then if you follow this dark line, yellow phosphor. So the blue light of the blue LED excites the yellow phosphor. Combination of a blue and yellow make you think that you're seeing white light. In fact, if you look at your skin, it looks a little pasty because there's no reddish tones in the light. Nothing to reflect off of you to give you the hues that you're expecting to see. Well, so one way to fix that is to go ahead and take the very same light bulb with blue and a yellow and put right on top of it this quantum dot film, quantum light optic. What it's going to do is the blue light will diminish, and hence why we have this less blue light. And that blue light will diminish because it's absorbed by this film. And this film, after absorbing the blue light, luminescence its own color, which is red. And hence I can get the blue, the leftover yellow phosphor, and here is the red peak. How does that compare to a black body radiation? A lot better than I saw it before. This metric of color rendering is a metric that tells you how well can you match the incandescent light bulb, let's say. And it's not any number greater than 90. It's indistinguishable from an incandescent light bulb by your eye. Another way to test it is actually to take a same scene and illuminate it by 3 different lights. Incandescent light bulb, cool white, this is a blue-yellow LED, and then a quantum dot enhanced one. Notice that bananas actually are ripe, despite the fact that under the LED lights they might not appear so, because you are missing the actual red hues. So this was done by economists. They came to Q Division, the little company that started to commercialize this technology. Q Division took this technology from Wendy's lab and our labs and started asking themselves questions on can they actually go ahead and make entirely new ways of thinking about uses of nanomaterials. They figured out now how to scale the making of the quantum dots to the gallons and gallons levels. And you can indeed make these light bulbs that used to be commercially available. They can still be if another factory comes in and plays with them. But for right now, they're looking at ways of using those very same quantum dots in another market. Before I go to the other market, let me just show you quantification of the value of the enhancement of quantum dots inside these displays, inside these light bulbs. And that is here I'm showing you color rendering. That's to say how well can you match the incandescent light bulb. Here's incandescent light bulb, really well does in matching incandescent light bulb. But it's not very efficient. Luminescence efficiency, unit of lumens is perceived brightness. How bright something appears to our eyes. You know, if I shine infrared light at you, no matter how bright it is, you wouldn't know it. So that's 0 luminance. But any visible light will have some amount of fixed luminance. You want to have a lot of luminance for the number of watts you spend running the light bulb. You'll notice there's a trade-off. Every light bulb, and you can just go to bulbs.com and just download the data. That's what I've done. Bulbs.com, just download the data and all the available LED light bulbs. And you'll find a trade-off between efficiency and color quality, except for 2 of them. Here is the L Prize winner. This is a Philips L Prize winner, 90 lumens per watt. You know what? You can't buy these in stores. You have to special order these. They cost a fair bit of money. What you can't buy in stores are these. These utilize a much less sophisticated phosphors and have sacrificed color conversion quality for the sake of cost. Well, these don't cost very much whatsoever, yet will give you one day this efficiency if actually you work with the optic of the bulb manufacturer rather than just slapping it on top of today's light bulbs. It's a market of $20, $30 billion, right, lighting, but one that's divided among maybe 100 different players. So it's hard to capture it unless you work with really big ones. But the big ones are really hard to move. Companies like Philips or GE are very circumspect about adopting an entirely new technology. So is this a best way for a small company to launch a product? First one, and first commercial use of quantum dots indeed is valuable. But maybe another thing to ask, well, can I use them elsewhere? And the one question first you need to go and ask is, how long do these live? Well, through the magic of chemistry, they live a very long time. I'm showing you here the operation of those light bulbs as a function of almost a year. And they don't get worse. They actually get slightly better from the first time you turn them on to when we finally stop measuring. So what's the lifetime of this quantum dot phosphors? I can't tell you. I mean, we can try to accelerate the aging, but they just keep on getting better, for all we know. There is a way to kill them. The way to kill them is to really cook them, but you need 300, 400 Celsius. That's when you start decomposing them, but you would start decomposing at the temperature as well. So, it's only fair. So a better technology to go ahead and ask, where can I insert my quantum dots into? Well, maybe it's, rather than $20, $30 billion lighting, maybe I can somehow affect the $110 billion LCD technology. That's a good chunk to persuade a VC to invest in, right? And you look at the very same quantum dots and you say, well, can I somehow affect the LCDs? So if you look just over here towards me, just to give you a little lesson on the LCDs, LCDs have an image that I'm seeing right now. And that image is generated by there being liquid crystals in front of me. And those liquid crystals are illuminated by light from the back. That light actually sits on the bottom of the display. There's a little tube on the very bottom of the display that pipes the light up in what's known as a light guide, a piece of plastic. That light guide scatters the light towards me, through the liquid crystal, through the color filter, through the polarizers, towards my eye for me to see the image. But the start is that light bulb at the very bottom of my display. Today's light bulb at the bottom of my display, here it is, an image of it, and it's shining light that is piped up into the light guide, eventually to come towards me. That light bulb right now emits the following spectrum. That's this light blue line. Blue LED with a broad green phosphor and broad red phosphor. That's what you have as an option. As a result, if I want to show you a red image, a perfectly pure red image, I can. All I need to do is make sure that this white light passes through a color filter that narrows all the photons to only the few ones that look perfectly red. Well, if I did that, really, if I really did that, my battery wouldn't last very long because I'm only passing the smidget of my entire light spectrum. As a result of that, I'll be throwing away a huge amount of energy. And that's not the best way to go if you want to have a portable device. You know what I'm going to do as a manufacturer? I'm going to broaden that filter. So rather than just give you the red photons, I'll give you a bit of an orangish red. You won't notice. Among friends, what's a little bit of extra orange? And so for the green, rather than having pure green, there'll be a little bit of yellow green and a blue green. I'll do that. I'll diminish the color quality because I'm trying to save on the energy. Except, what if I can come by and say, listen, I can give you a much better light bulb. One that has red, green, and blue that consists of entirely pure red, green, and blue colors, rather than this broad spectrum like I'm showing you right here. And the way to do that is start with a blue LED and the narrow emitting green quantum dots and the narrow emitting red quantum dots. And the way to do that is just rip out your present light bar with a blue light bar and a little tube, glass tube, filled with quantum dots. That's all you need. You don't need to change your display a bit. Keep it exactly the same. Keep the same color filters, because you know what? You can pass as wide spectrum as you want. The only colors you're going to get from me are the pure reds and the pure greens. I don't have any orangish red to give you, or yellowish green or bluish green, because my quantum dots emit very, very narrow emission. So this is a very simple way and very simple decision for companies like Sony to actually take this technology. It's branded under Color IQ. If you go to Best Buy or Fry's on the West Coast and look for the best looking TV, you'll find that it's Sony Bravia. And if you look at the quality of color, it's so-called triluminous color technology. That's the quantum dot technology. There are about 1 million units sold since May till today on the market on 3 continents, Europe, Asia, and North America. It did actually get exhibited during the Consumer Electronics Show in January 2013 in Las Vegas. And out of the tens of thousands of products, it was selected as the best product award. Because it looks so cool. I mean, it looks amazing. If you come to my office, I'll show it to you. It looks really good. It does. I just had to have one. So it turns out that the technology itself right now is commercialized in Lexington, Mass. The quantum dots are made there. They are in gallons shipped to Taiwan, where the tubes are filled and then delivered to Sony as a technology you can just slot in. There are 150 jobs in Lexington, Mass. There are about 300 jobs in Taiwan that are generated through the crazy idea we started 8 years ago now called Q-Division. Now, this is optical excitation of dots. And I'm looking at my time, and I want to just show you a couple of more examples. Rather than just doing optical excitation of dots, the other thing you can imagine doing to allow them to be deployed on as extremely thin surfaces is to take these very same quantum dots and load them in an inkjet printer. And go ahead and print wherever you want active luminescent surfaces. So this is an example of 75 micron droplets of green quantum dots, cadmium selenide, that are able to, depending how small of a nozzle you have, you can print down to microns, few microns if that's what you want. For a display that is the size of my display, accuracy of 25 microns is plenty. 75 microns for a big HD TV is plenty. So this is small enough, but we can do better through the developments of that, let's say, Cativa is developing. But go ahead and load it with, let's say, red dyes, and you can inkjet print it on top of AC tin film electroluminescent piece of plastic. This is the same stuff that's used for night lights in your bathroom, maybe. A little glowing blue sheet. You can inkjet print on top of that, and you can convert that blue light into the green and the red of the quantum dots and get full color triangle you expect of a typical display. But this is not a pixelated display. This is just a show-off that I can give you a glowing sign that glows different color. Maybe I can make a really cool display by actually doing the same thing I did with OLEDs, which is take a device and look at the heart of OLED. I said that middle 10 molecules is what's glowing in an OLED. Well, let me rip those out and replace them with a monolayer, a thin layer of quantum dots. Quantum dots are great because you can go ahead and make them optically excited. Can you make them electrically excited? And the answer is absolutely yes. If you take a pickle and you plug 2 forks in it and plug it in 110 volt outlet, you'll get it to glow yellow-green. Don't do it at home. But that's no different than what we're doing here. All OLEDs are is just a pickle sliced really, really thin. So you can get away with 5 volts rather than 110. Really, that's all. You need the same kind of high fields. And all that quantum dots are the same thing, a little chunk of element of matter that is naturally willing to luminesce. If you engineer exactly right the device so you don't have too many holes versus electrons, you should be able to make it to glow even under electrical excitation, not just optical excitation. And images on the right show you that. This is the solutions that we start with. We make them into these kinds of stack and apply 5 volts, and you get a glow. Here is the different colors that come from these solutions. As a matter of fact, you can make them larger in area. You can make them flexible if that's what you want to do, so that you can go ahead and say, hey, my light bulbs indeed are not like I've just shown you, but they maybe look something like this. This is your light bulb you might see not too long from now. There it is, a piece of plastic, about 5 volts, electrically excited layer of quantum dots. What's the state of the art of this technology? Well, we published this year the best quantum dot LEDs. There are, here I'll show you them. This is so-called 18% device. It is 18% external quantum efficiency. What that means is that for every 100 electrons coming in, I'm seeing 18 photons. The thing is that about 82 photons actually stay inside a piece of glass and never make it out due to the Snell's law. So these devices are actually 90% efficient. 72 photons stay in. Internal efficiency is about 90%. And we can scatter out a whole bunch of extra light with tricks. However, we didn't want to do that. We want to show vanilla technology without any trickery applied to it. This is the world record by factor of 4, better than any other quantum dot LED ever made, and indeed close to 100% internal quantum efficiency. It's only done in red. So I look at this technology and I say, well, this is the very early days of quantum dot LEDs, because one day these actually could replace OLEDs as we know them. Right now, quantum dots are in LCDs, and I can see that the white lights of LCDs will be replaced with quantum dot enhanced structures. OLEDs, due to the power conversion efficiency, once the printing technology is standardized 5 years, 7 years from now, OLEDs will be ubiquitously deployed just like LCDs are today. But then quantum dots, they just happen to be a pure color more tunable, a little more stable possibly, OLEDs down the line. That seems like a more interesting technology to look towards, and I can see them being as a complement of OLED technology, yet an entirely different technology, patent-wise, from anything that OLEDs have ever done. OLEDs are a very large business today, $10 billion, going on to 20 or 30 in a few years. Very large business that's entirely enmeshed in a patent struggle between LG and Samsung and Sony and Philips and the others. Q Division is one-stop shopping for QD LEDs. And yes, it's a brand new technology, but in 5 years, it can actually start being competitive with OLEDs. An intriguing proposition to look at, especially because beyond the visible color, you might also be able to reach, well, how about you can also be able to reach infrared emission that you cannot do with molecular dyes. So if you choose to make infrared devices, you can. It's again through the trickery of chemistry. But the best one we've done, this is not yet published, but among friends, I don't mind sharing. These are 8% efficient devices, again, by a factor of 4, better than anything else ever demonstrated in any flat panel infrared technology ever made. So I think it's intriguing, especially because this is a 1.3 micron light. 1.3 micron light can go through your skin. And so you can actually image stuff underneath your skin that you would not be able to see otherwise with visible light. That's kind of cool. Let's say if you have one of these on your cell phone and you have an infrared imaging camera, which we can also do using the quantum dots, you might be able to go ahead and take, your cell phone and go around the grocery store and find the apples that have been bruised. Because the light will go through the skin and through the nice shine on the outside and actually show you the underlid, as an example, if that's what you're after. I'm looking at my time, and I would love to tell you many, many more things, because indeed, ubiquity of opportunity is just vast. I think what you're about to see, and by about I mean over the next 5, 10, 20, 50 years, is indeed deployment of entirely new paradigms of what technology is. And it will all be enabled by the uses of nanomaterials. I do want to get to my next slide over here, not this one, because this is an entirely new story. Really cool things you can do. You can print membranes over very large areas, and they can move. Here is a video of them moving. Oh, that's kind of cool, mesmerizing in its own way. Actually, you can make, with these membranes that move, you can make speakers that are as thin as a sheet of paper. We've done that. And you can make them a millimeter big if you want to stick them in your ear, and you'll hear this level sound. If I make them 10 millimeter squares, 3 by 3 millimeters, stick them in your ear, it'll be ear-splitting sound. And the amount of energy you can use, factor of 4 less than the conventional headphones. Kind of cool. Maybe you can power those with glasses that have transparent solar cells on top, right? That'd be kind of cool. You never have to replace, the batteries in hearing aids if that's what you're after. There are options and options to look at. But I do want to highlight just one last thing, which is that much of what we do at MIT is not done by us, faculty, but it's actually done by people that are in the trenches, students. We only have 2 products, knowledge and people. And our better product is our people, right? There are 125,000 MIT alums. And if I go ahead and ask how much value have they generated for the world, in 2002, the census said that about $3 trillion was the worth of the companies started by MIT alums, faculty, and students. That generated 3.3 million jobs. It ranks as number 11 as an economy of the world. If you look at the patent productivity, about 2% of all the patents issued in the United States have an MIT alum on them. About 10% of all the patents utilized in the world have an MIT alum on them. We are much more efficient in delivering useful technologies. So the next thing we need to do, because you do recognize that everything we do at MIT is 1,000 flowers bloom, and we have many opportunities. We are looking at developing a space central to the campus here. It's going to actually be at the heart of campus, right next to the dome. And we are calling it MIT Nano. You might know where Building 12 is. It was built by the Department of War, and it still stands. Department of War doesn't exist anymore, right? It's a fairly old building. It was the initial home of Chemical Engineering Department. It's also a place where Microphotonics Center has housed some illustrious alumni. But the next thing to do is to tear it down. and to build the next facility in it. Our present micro nanofab that I used to direct as of 3 weeks ago is twice as busy per square foot than any other micro nanofab in the United States, in any university of the United States or the world. And actually twice as busy both per square foot and as number of hours. We are so busy that actually we send our people up the street to Harvard. Half of the external users of Harvard Nano Facility that opened in 2005 are MIT students and faculty. 10% of all the income that Harvard facility gets is from MIT. And that's fantastic. You know, we need partnerships. We love our partners up the street. But at the same time, we realize that we can dramatically improve our own productivity by generating a new facility. And the one that they asked me to go ahead and build, or at least figure out how to build. So since 2011, I've been working with fantastic architects in imagining what this place can be. And one thing that we laid out at the very beginning, we said, well, this is so central campus. There's no need for any faculty to have an office in this place. There's no need for any student to have an office in this place. As a matter of fact, there's no need for anyone to have a lab in this place. What there is a need is to have a common space, a common facility for all of us to get to, like we are right now doing in our micro nanofab. So we are building 2 floors of clean rooms that will about double our clean room capabilities, a large floor of imaging that will double our imaging capabilities on the nanoscale. Very quiet, very clean. Why? Because dust particle is as big as the device I'm trying to look at. Very quiet mechanically and electrically. And then on top of that, on top of the whole structure, up on the top where things start wiggling a little bit, go ahead and then develop a prototyping facility and a synthesis facility, place where you can make these nanomaterials in a beaker and actually translate the ideas from those labs and the clean rooms into things you can hold in your hands, and hence launch the products into real world values. This is a crown jewel in a necklace, or call it a crown, of innovation initiative. We see this nano innovation space that is what we call MIT Nano as the key to what we need to develop. President Reif and the corporation is strongly behind it. We're going to start tearing down first things in summer, this coming year. First time we'll start building things is January 2015. January 2018, we hope to open the doors to a new facility that will likely be operational over the spring 2018, about four years and 4 months away from today. So if you have a starting freshman at MIT, by the time they're ready to be a graduate student, this will be ready for them. So I'll stop right there. I thank you for your attention. I'll be glad to answer any questions you might have. Thank you. Yes.
I was just looking at your all the applications you showed us. No doubt, very few compared to all that you thought about, and thought about this notion of the Hancock Tower and doing that very large surface with essentially dots of some sort sprayed or put into materials. Can you do this with flexible materials too that endure in hard conditions? I'm thinking of laying this down for all the interstate highways in America and having very large solar collector systems that are ubiquitous and may even reduce the amount of time we need to repair all these asphalt roads. Is that a possibility?
Yes. I'm not sure I would do it exactly like that. But I think you're on the right track, absolutely on the right track. I can look at any surface and say any surface is available to me, a road or a window. You'll abuse your window a lot less than you'll abuse the road. And you know what? If you make a new window, it's a double pane window. It already provides me packaging that protects the cell from additional damage. If I can come up with a wireless energy transfer from that window to a hub nearby, maybe I can use Witricity technology developed by Stolyarchik, Jonopoulos, and others, I can come up with a way not to avoid even wires that I need in a process. I mean, so and surfaces of windows are quite large. For me, if I start building today, it's going to take a long time for me to populate all the windows of the world with these cells. Roads are a fantastic option as well. As a matter of fact, I'm very excited about roads because it turns out that I need about 0.3 to 0.5% of the United States to be covered with solar cells to provide all the electricity of the United States in form of solar. Now, that's an unfair thing to say, only because at night there will be no electricity, right? So without storage, this is really not necessarily the way to go. But good news, kind of. The good news is that if I look at the just dramatically rapid pace of deployment of solar, 40% increase from year to year to year, in 10 years, I'll be able to meet 10% of electricity needs of the United States. So it's going to be about 2 decades at this astronomical pace that I might be able to meet all of the needs of the United States, only if I have the battery system to serve as a storage. All right, so that's one thing to keep in mind. 10% is kind of the metric that I say, let's stop there, because the grid can serve as your backup. There will be a gas-burning power plant on the grid somewhere nearby my solar installation to back me up at night, right? If I go beyond 10% penetration of solar, then that's, poor coal operator will have to turn down because he can't make any profit, right? So it's 10% is my ceiling. Roads are a really easily deployable surface. We know how to do roads. The biggest thing we ever built as a humanity, right, is a road system. 2 to 3% of all of the surface of the United States is covered with roads, primarily in the cities, but also highways, right? And I just mentioned that I need 0.5% to cover with solar cells, right? Now, mind you, we use 40% for feeding ourselves, 20% for the crops. A lot of it is corn that we don't actually eat. We kind of try to convert into ethanol for some reason. But the 20% is to feed the cows and the sheep and the goats. 20% for the cows. I'm just saying, if I can take 0.5% back from the cows, I can deploy my solar cells. That's one way to do it. The other way to do it is to say, well, there's plenty of land around the United States, around roads, that no one really wants. You don't want to build your house next to a road. It's too noisy. There's easement land. There's about 50 feet or more of easement land around all the major highways. That's a lot of land. It happens to also be the land where we pass all the power lines, because that's convenient. Oh, that's what I need to hook into if I'm going to have a solar cell. It seems like a possibility to utilize an undeveloped, purposely, no one wanting undeveloped land, to actually make solar installations that do matter. That's one way to do it. The other thing to mention, since you mentioned roads, is to ask, if I want to actually make a cost-effective solar cell, and I want to do it by using conventional panels, what is the cost and speed at which I need to deploy my solar panels? Well, if I could deploy my solar panels as fast as I pave roads, in 10 years, I would meet 10% of the US electricity needs. Oh, and by the way, besides the speed of deployment having to match the speed of paving the roads, the cost of deployment also better match the cost of paving the roads. Because it's $1 million for, $500,000 for 11-foot wide, 1 mile long lane of highway in Florida. Comes out to 64 cents a peak watt if this was a 15% efficient cell. That's all the money I can afford to spend and still give you cost-effective electricity. So maybe I can change the paradigm of deployment by saying I'll give you, rather than a panel that's a 1.5 meters squared, yay big, it weighs typically 40 pounds, and hence labor laws tell me I can't allow anything heavier to be lifted in a repetitive fashion by a worker. So that's why I cut it to 1.5 meters squared. Maybe I can give you a roll that you can just unroll on top of your roof, staple it, and you're done. That's a different way of deploying. And so I think we can reimagine what we mean by solar energy. Everything I showed you here today is a pipe dream right now. Anything hardware, anything, takes 7, 8 years to reach large-scale commercialization. In 3, you can make first gizmos. 2, you can make first gizmos and make large profit margin on small volume. Anything large, at least, give me 7 to 8 years. Velcro took 17 years to catch on, right? So please give me at least half of that. And it turns out that anything you look around that is hardware developed does require $50 to $100 million to go from the beginnings to the large-scale deployment capability and profitability. So there's a lot of stomach that VCs and others who choose to invest in this kind of thing need to have. And we are unfortunately, as a society, choosing not to invest in hardware very much anymore. Loose and closed or is not quite what it used to be. Yorktown Heights, IBM, again, not quite what it used to be. IBM Almaden, again, not quite what it used to be. HP Labs, pretty much software directed. Xerox, again, primarily directing toward, ask who is making hardware for tomorrow. It's a big problem. And so I look at what we are doing here and imagining this MIT Nano, and I look at, for example, just as an example, you look at profits of Apple. A day and a half of profits of Apple would be sufficient to ensure 30 years of innovation. Now, is that an insurance policy? It seems like a rational insurance policy to me. As I look at Qualcomm, look at Dropbox and Facebook. Look at companies that are looking at ways of advancing new innovations in a soft world, really important world. Facebook is a fantastic innovation, but it rests on developments of new hardware. And who's going to make that? Who's going to make the next switch? Because you know what? I'll give you one more tidbit. I'm going to ask another question, or let you ask me another question. So it turns out today we spend 1.5% of world electricity on running cloud computing. And we like cloud computing because everything's convenient. I don't have to update my software anymore. As a matter of fact, I like it so much that people predict we'll have a 1,000-fold increase in cloud computing in the next 10 years. That's 1,500% of world electricity that will be needed to run cloud computing. That's not quite rational because it took us 150 years to make today's energy generation capacity, so I can't quite see us going up that high. But besides that, I just can't quite see us sticking with the same paradigm of switching. How much time do we have? We have 10 years. Well, when do we need to invent the switch? Well, tomorrow, because it takes 5, 8, 10 years to actually commercialize it large scale. We have some ideas, but they involve photons, not electrons, or spintronics, or excitonics, really exotic stuff that I'm not sure companies are looking into, but universities are. And so if I ask where is the next innovation factory for what is 21st century will bring, has to be, the way we're designing the world right now, it has to be universities. Because the big companies simply can't afford to do it. And the ones who are able to afford it are the ones who are taking already existing technology and adapting it for new social structures. And indeed, they can do that for the next few years. But I'll ask you 5 years from now, where is going to be the new switch or new display? Probably from Samsung, because they'll choose to advance it. Yeah. Yes, please.
You spend quite a bit of money. If you buy a window with a high R value.
Yes.
You see, so if you say, do a trade-off, if I can generate electricity at a lower R value, can I give effectively the same performance? I just wonder if it might be a useful comparison.
It's a very useful comparison. And as a matter of fact, the right thing to do would be to say, what is the cost in cents a kilowatt hour? Yeah. And if I can make my solar cell last 10 years, I'll be at about 11 cents a kilowatt hour, which is cost competitive today, even with a fairly inefficient technology, which is cost competitive with coal and gas generated, even hydro generated electricity. So yeah, no, I appreciate that, and I appreciate you mentioning it for me.
I think we need to end. We've gone over quite a bit.
Oh.
But, I want to thank you all for coming, and hopefully you'll come to the next one. If your company might be interested in sponsoring, we'd appreciate that too, and we could then lower prices. So that would always be good. I wanted to thank Professor Bulovic so much, Dean Bulovic, and thank you all for coming. And there's dessert and coffee in back, and the bar is going to be open for a short time. I'm not sure how long. So we're going to stand in line. Thank you.
Thank you. Thank you.
Thank you so much.
My pleasure.
So this is for you.
Oh, well, thank you so much.
Some whiskey glasses. Hopefully you'll use them.
Of course. Of course.
You mentioned a company several times. Is that you?
They're all my companies. So QQ Division is the first one. They are now biggest.
Okay.